Hello everyone, my name is Fireaizen and I am happy to present to you, distinguished guest, the work of our team on intelligent reflective surface configuration using adaptive quantization and neural prior. The work was done in the SIPL laboratory in the Faculty of Electrical and Computer Engineering at the Technion, Israel Institution of Technology, and in collaboration with the Faculty of Electrical Engineering at Tel Aviv University. Our work dealt with the tuning of intelligent reflective surface, or IRS, which are two-dimensional surfaces that contain a large number of tunable elements that change the amplitude and phase of the signal returned from them. This technology is innovative and can help overcome attenuation problems that may develop in high-frequency communications, such as the sixth-generation communications. It is natural to compare the IRS to relays, which are active devices that decode and retransmit the received signal. However, the IRS is better than the relay in that it is passive and therefore does not increase the received noise. It also has a higher energy efficiency and even leads to better results on large surfaces. The system model can be seen in this image taken from the IEEE 2021 Signal Processing Cup Competition Guide, courtesy of Professor Emil Bjornsson. A base station transmits a signal that hits the IRS and is returned to the user after it has been modified by the IRS. The IRS make it possible to overcome the fact that there is no line of sight between the user and the base station. In contrast to most of the work in the field, in which the communication was based on narrowband transmission, in our model we used OFDM wideband communication. In this model, the signal received by the user is given according to the following formula. When Z is the received signal, HD is the direct uncontrollable channel, VA and VB is the indirect channels between the base station to the IRS and between the IRS to the receiver respectively, Theta is the phase shifts given by the IRS configuration, X is the transmitted signal, and N is an additive white Gaussian noise. All of this is given in the frequency domain. The uniqueness of our work is further reflected in the fact that our model is based on an IRS with two states only. Each element of the IRS can give phase shift of 0 or pi to the signal reflected from it. Also, the elements cannot change the attenuation of the signal returned from them, just phase shifts. In our system, we have 51 users. All of them are not in line of sight to the base station. Some of them are in line of sight to the IRS and some are not. Those who are in line of sight to the IRS will be called N-loss users, and those who are not will be called N-loss users. The problem description is to find the best configuration that maximizes the data transmission rate for each user separately. In this presentation, we will briefly review three solutions to two major problems in using this system. The first problem is the channel estimation problem, to which we will briefly present a solution. The second problem is the problem of finding a good configuration of the binary IRS, to which we will present two solutions. One solution is based on adaptive quantization, and the other one is based on an innovative deep learning format called neural prior. Our work began in response to the challenge posed by the IEEE 2021 Signal Processing Cup competition. This is the most prestigious signal processing competition for undergraduate students from all over the world, in which they deal with real problems from the world of signal processing. This year, the goal was to characterize the behavior of this system and develop a control algorithm to find the ideal configuration so that the highest data transmission rate is obtained for each user. Our system consists of an IRS containing 4096 binary elements, and a new dataset that has 4096 IRS configurations and the signal received from them for 50 different users. The pilot signal is constant, and when each configuration is arranged in a column, the matrix generated from stacking them side by side is an Hadamard matrix. Examples of low-ordered Hadamard matrices can be seen here on the bottom of this slide. It is important to note that the summation over the rows of the Hadamard matrix gives 0 for all the rows except for the first one. The IRS has only been under investigation recently, so there is relatively little previous work on the subject. Several heuristic solutions have been proposed to solve the problem of configuring the IRS phases when the phases are continuous. In our solution, we will use the solution proposed by Zheng and Zhang in 2020, which is based on maximizing the information obtained in one tap of the OFDM transmission. This solution is called the STM solution, strongest tap maximization. It is important to note that this solution assumes continuous phase shifts of all elements in the IRS and therefore does not meet our problem definition. Few solutions have been proposed for solving a binary IRS problem, and most assume the possibility of controlling the attenuation of the reflected signal from each element on the surface. In our system, the IRS is passive, so it does not transmit nor receive signals itself, and all channels need to be evaluated using signals sent and received at the base station or the receiver. Therefore, an estimation of channels VA and VB is not practical, and the cascaded channel V from the base station to the IRS to the receiver should be estimated instead. Due to the shortness of time, we will present here only a simple least square estimation, in which we first estimate the direct channel from the base station to the receiver. As can be seen in the first equation, averaging all the signals received by one user will give us his direct channel, plus the channel that passes through the first element of the IRS. This is a result of summing over all the rows of the Hadad matrix gives 0, except the first row. The effect of this channel is relatively negligible, so it can be said that it is a good estimation of the direct channel. The cascaded indirect channel V can then be estimated in the way presented here and in our paper. A more accurate and better estimation of the channels that uses the understanding of the spatial structure of the IRS is presented in the paper, and we encourage you to review it. In this graph, you can see the amplitude and phase of the signal received by the receiver and its estimation result. The estimator is close to the ground truth, with the differences mainly because of the effects of a wideband transmission. We will now move on to discuss the problem of finding a good configuration for the binary IRS. The following optimization problem can be defined as we will search for the configuration theta that maximizes the data transmission rate, under the constraint of the binary IRS, only 0 or pi phase shifts. This problem is far from convex, so standard optimization algorithms like gradient descent will not work here. Brute force search algorithms will not help either, as there are a huge number of possible configurations. To start explaining our first solution to this problem, we will present a simple quantization of a solution for the continuous phase shift case. In this case, we will use the STM strongest tap maximization solution to find a good continuous phase configuration. One can be seen in the figure, and quantize it along the best separation line that also can be seen in this figure in red. The separation line is found by an exhausting search over all the possible angles and measure the resulting data transmission rate acquired by the quantization along the suggested line. A better algorithm than the naive quantization is the following adaptive quantization algorithm. This algorithm composed from repeating of two steps: quantized one element and perform gradient descent on the element that remained unquantized. In detail, we take the element that we are least confident in its labeling and create two proposals. Either it will be categorized as +1 or as -1. To each proposal, we perform a gradient descent on all the non-quantized elements and check which proposal received a higher data transmission rate. We select this proposal to continue the data quantization process repeatedly until all elements are quantized. Our second solution is based on a new approach we took from the field of image processing. The found in article Deep Image Prior suggested using untrained deep neural networks to solve complex inverse problems such as artifacts removal and in-painting images, as can be seen in the illustrations at the bottom of this slide. This idea to use deep neural networks as an optimization tool without actually learning mapping from samples is causing many echoes in the world of machine learning, and numerous new articles on this subject have been published recently. To solve our problem, we will act according to the following scheme. We will define our loss function as minus the data transmission rate. Then we will initialize our deep network weights randomly. And we will randomize a vector of random Gaussian noise that we repeatedly insert into the network, so that at the output of the network we will get a valid IRS configuration. The weights of the network are optimized, and not the phases themselves, that in contrast to the previous solution. We will repeat the optimization process until the network converges. Our network's architecture consists of two parts. The first part received 64 times 1 random noise vector and yields a 64 times 1 vector that then repeated to create constant columns configuration. Then, we insert this configuration to the second part, which is a convolutional neural network that's used to fine-tune the configuration. An example to the output of each step can be seen at the bottom of the slide, and the reasoning for the selection of this architecture is given in the paper. We used the principles of overparameterization to avoid local minima points, as explained in the paper, and hyperbolic tangent activation functions to keep the phase shifts in the valid area. The quantization part happens in the output of the network. We saw that loss users tend to have constant columns configuration and receive higher data transmission rate from the neural prior solution than from the adaptive quantization. However, the n-loss users receive lower data transmission rate from the neural prior and tend to have more messy configurations. Thus, we suggest a third solution that combines our first two solutions. We first create an azimuthal columns-like configuration using the first part of the DNN. Then, we estimate the elevation part from the adaptive quantization configuration and combine them to one new configuration, as can be seen in the figures. The result of all users are given in the graph shown here. As a baseline, we use the highest rate achieved by one of the configuration given to us in the dataset. As the highest possible point, we use the rate achieved by the STM configuration with the continuous phase shifts. Our solution is been in black triangle in the middle for each of the users. This table shows the average data transition rate achieved by each method for loss and n-loss users. It can be seen that the use of the IRS significantly increases the data transmission rate, and that the right choice of configuration can lead to 40-fold increase in it. For loss users, we gather the most efficient algorithm is neural prior, and for n-loss users, the combinations of the two algorithms led to the best results. So, to sum up, IRS is a recent promising technology that can improve the data transmission rate in 6th-generation communications. We have shown a method for channel estimation using the shape of the pilot transmission and offered a better novel algorithm in the paper. We have presented 3 novel algorithms for configuration optimization, using adaptive quantization, using the first use of neural prior in the IRS field, and a combination of the two algorithms using azimuth elevation decomposition. We also received state-of-the-art results. We would like to invite you to check our ICC 2022 paper, which is currently under review, in which we extend our research on the neural prior solution to the continuous phase case, and show state-of-the-art results. We would like to thank you all for listening, and have a nice day.